Welcome to our video lesson for section 2.4, complex numbers. Today we're going to be talking about complex numbers. We're going to be combining them using algebraic operations and simplifying them. Let's get started. Let's start with defining imaginary numbers. An imaginary number is a way to represent a negative number underneath a radical. The foundation for this is going to be the square root of -1, which is always going to be defined to be I. So as we are simplifying things, if we can somehow simplify out the square root of -1, we can transfer that to be an I, and then we can manage what is left. Let's see how this is applied when we have our first example of the square root of -6. I want to somehow break that up so I can get the square root of -1. If I could do that correctly, then I could see I have the square root of 6 and the square root of -1. And notice we've already defined the square root of -1 to be I. So for my final answer, I have I and then the square root of 6, which is left. For our second example, we're going to split things up in the same way. So I have the square root of 16 and the square root of -1. Again, we have defined the square root of -1 to be our I value, and hopefully we know that the square root of 16 is going to be 4, and that's how I get my final answer. So by breaking things up in this way, it makes the problem a little bit more manageable and easier to see where our I comes from. Let's look at a few more examples. First, I have the square root of -7. With my previous examples, I broke them up, so I'll do this as well for this one. I'm going to have the square root of 7 and the square root of -1. We know that the square root of -1 is defined to be I, and I can't simplify radical 7 anymore. So for my final answer, I have I radical 7. And it's kind of important to put the I in front of the radical. That way we don't confuse it with being underneath the radical sign. For our next example, we'll do the same process. So I have the square root of 12 and the square root of -1. Again, we know radical -1 is going to be I. And I can simplify radical 12 to be 2 root 3. So this whole thing will be 2I root 3. And then for my last example, again, the negative sign is going to become I. I can't simplify radical 15, so I'm just going to have I radical 15 as my final answer. A complex number is any number that contains both real and imaginary numbers. The standard form of a complex number is going to be A plus BI, where both A and B are real numbers, and I represents the complex or imaginary portion. Every number can be written in this form. If we don't have a real value for A, we can include it as a 0. Same thing for a complex, we could have a 0 for B, but usually we're going to have at least both components. All right, for our first two operations, we have addition and subtraction. For any two complex values, A plus BI and C plus DI, we're going to combine them by adding like terms. So we can see A and C are the real portions, and then B and D are part of the complex or imaginary portions. So when I'm adding them, I just add the corresponding parts together. Same thing with finding the difference. I would be subtracting A and C or subtracting B and D because I'm just trying to combine like terms using the operation that's been stated. Let's try this with a few examples. All right, so we have some expressions here we're going to try and add together. To begin with, we have 3 plus 5i and then 4 minus 3i. I want to combine like terms. So I notice I have a 3 and a 4. Those are the real portions. If I'm adding those together, then we're going to get 7. And then for my imaginary portions, we have the 5i and the negative 3i. If I add those together, then I get plus 2i, and that's the simplified expression. If I look at my next examples, we have 4 and then negative 3 plus 7i. Again, we're going to focus on combining the real together. So I have a 4 and a negative 3. If I add those together, we get 1. For the complex portion, we don't have any I values here for our first expression. For the second one, we do have a 7i. So when I add them together, I simply just get plus 7i. And for our final example, now we're going to be doing some subtraction. Again, we're going to line up like terms. So I'm going to start by subtracting the 2 and the 3. I'm going to do 2 minus 3. So in this instance, we're going to get a minus 1. And then I'm also going to pair up the negative 4i and the positive 2i. If I subtract them, negative 4i minus 2i is going to end up being negative 6i. When we multiply complex numbers, we multiply the exact same way we do any kind of algebraic expression. We're going to use the distributive property. So I'm going to multiply 3 times 3, 3 times negative 2i, 4i times 3, and then 4i times negative 2i. All right, so let's go ahead and multiply that out. We get 3 minus 6i plus 12i, and then minus 12i squared. When I combine like terms, we have 9 plus 6i minus 12i squared. All right, now something very important to note here, because I is equal to the square root of -1, that means that I squared is going to equal negative 1 itself. So for my last term there, I do have a I squared, which means that this whole thing is going to end up just being negative 12 times negative 1, which ends up equaling a positive 12. So I have 9 plus 6i plus 12, and the whole thing will then simplify to be 21 plus 6i. When discussing complex numbers, we also want to bring up the idea of the conjugate. To identify the conjugate for any given complex number, starting with a plus bi, we would use that to find the conjugate and identify it to be a minus bi. So let's look at what the differences is. The only difference between the original and the conjugate is the sign in between. We start with a plus bi, and notice for the conjugate, we now have a minus bi. And that really is the only difference. So when given a complex number, the way we would find the conjugate is you would change the sign in between the real and the imaginary portion. Let's go ahead and discuss what happens when you multiply a value by its conjugate. So we're going to multiply the same way we did with our last example. We're going to distribute. So we have a times a times negative bi, bi times a, and then bi times a negative bi. When we multiply that out, we get a squared minus abi plus abi, and minus b squared times I squared. All right, we can see that the minus abi and the plus abi are going to cancel themselves out. And we discussed in the last example that I squared is the same as negative 1. So when I multiply negative 1 times a negative b squared, I now get a squared plus b squared. And this is always going to be the case when we're multiplying a number by its conjugate. We can just take our a and our b values, square them, and then find the sum. All right, for the next two examples, we're going to identify the conjugates and then multiply them to verify our property from the last slide. So if I want to identify the conjugate, again, what I'm looking at is changing the sign in between the real and the imaginary part. Since I had a 4 plus 3i, to find the conjugate, I'm going to change that plus, and it's now going to be 4 minus 3i. If we look at our second example, we're going to apply the same property. So I start with the 3 minus 2i. Again, the symbol between the real and the imaginary part is a minus sign. So to identify the conjugate, I'm going to change that and make it plus, which means my conjugate is going to be 3 plus 2i. All right, let's go ahead and do some multiplying here. Going back to my first example, we'll multiply the two things together, and we're going to distribute. So we have 4 times 4, 4 times a negative 3i, 3i times 4, and then 3i times a negative 3i. All right, so we're going to get 16, and then we get minus 12i, plus 12i, and then minus 9i squared. We discussed the fact that I squared is, again, a negative 1. And we see, once again, that our two middle terms are going to cancel out because we have a negative 12i and a positive 12i. So when I simplify this, I'm actually going to end up getting 16 plus 9, which is equal to 25. And if we go back to our property from the last slide, we did discuss that we can shortcut this by just doing a squared plus b squared. Looking at your example, a is going to be 4, b is going to be 3, and if we do a squared plus b squared, we get exactly 16 plus 9, which is equal to 25. Let's verify that one more time with our last example. All right, so we're going to go ahead and multiply this together. When we do that, we end up getting 9 minus 6i, plus 6i, and then minus 6i, and lastly minus 4i squared. As with the last couple of examples, we're going to see those middle terms are going to cancel each other out. And then when we simplify, we get 9 plus 4, which is equal to 13. Again, we get plus 4 because I squared is equal to negative 1, and we end up getting a negative 1 times a negative 4 to become a positive 4. Looking at our shortcut, if a was 3 and b was negative 2, and I square them both, we still get 9 plus 4, which is 13. So from here on out, if you're multiplying something by its conjugate, again, we just kind of use that shortcut. Identifying a and b correctly, you can just do a squared plus b squared, and that would equal your simplified form of multiplying two conjugates together. All right, see if you guys can come up with the correct answers for the following two multiplications. For our first example, we have 2 plus 3i times 3 minus 4i. Note they're not conjugates. And then for our second example, we have 2 minus 4i times 2 plus 4i, and those are conjugates. So go ahead and see if you guys can select the correct two answers here. Once you have multiplied and simplified for our first expression here, you're going to end up getting a final answer of 18 plus I. And then for our second one, using our trick of a squared plus b squared, you should end up getting 20 as your final answer. And for our final operation involving complex values, we're going to talk about dividing. So when you divide complex numbers, you're going to be multiplying the numerator and denominator by the conjugate of your denominator, and this is going to help us get rid of I in our denominator. So a fraction is not considered to be of the right form anytime we have an I in our denominator, which is why we have to go through this process. For our first example here, notice that your denominator is 4 minus I. So we're going to go ahead and multiply both the numerator and denominator by the conjugate of that, which is going to end up being 4 plus I. We can use our trick for the bottom. We're going to end up getting 4 squared plus 1 squared, which is 17. And then for the top, we get 12 plus 3I. And that is, believe it or not, more simplified than our first expression. Final answer. All right, for our following two examples, we're going to do the same thing here. We're going to go ahead and try and simplify our expressions by getting rid of I in our denominator. For our first value here, we have 6 over I. And notice that we don't necessarily have a real portion for our complex value. We have just I. So if it helps you, you can kind of think of this as 0 plus I. So our conjugate is actually going to just be negative I. When we go ahead and multiply this together, we get negative 6I over negative I squared, which ends up just being negative 6I. For our second example, we have 2 minus I for our denominator. We do have an I in our denominator, which is the thing we have to deal with. Again, to do that, we're going to multiply both numerator and denominator by the conjugate, which in this case is going to be 2 plus I. All right, for our denominator, again, we can do a squared plus b squared, which would be 4 squared plus 1. Or sorry, not 4 squared, 4 plus 1, which is just 5. And then for our numerator, we're going to go ahead and multiply together to get 4i plus 2i squared. Once we simplify that, we end up getting negative 2 plus 4i divided by 5. One thing to point out here is we do always want to try and simplify our fractions. In order to do that, all three of our terms need to be divisible by the exact same number. So if I could divide negative 2, 4, and 5 by the same value, I would do that to further simplify our expression here. All right, for our final example, we have two separate fractions we're going to try and combine. In order to combine them, we need to get a common denominator, but first we have to deal with our denominator by going and multiplying by the conjugate of our complex values. So for my fraction on the left, I'm going to multiply both sides by, the top and the bottom by 2 minus I. For my numerator, I'm going to get 4i plus 2. And then for my denominator, I'm going to end up getting 5, again, using our shortcut of a squared plus b squared. For my denominator, for my fraction on the right, we're going to multiply by 2 plus I. And if I do that correctly, I should get 10 plus 5i also over 5 using our shortcut. Conveniently, our fractions both have the same denominator, so we can go ahead and combine things together. When I combine my two real components, I have the 2 and I also have the 10. So when I combine those together, I get 12. And when I combine the complex portion, the 4i and the 5i, we get 9i. And then divide that all by 5. Once again, we would look to see if we could simplify this further, looking at the 12, the 9, and the 5. Can I divide each of those terms by the same value? In this case, I can't, so that is the most simplified version of our expression. All right, guys, that does it for the lesson for this section. Go ahead and get started on the homework, and good luck.